Welcome to today's problem walkthrough. In this session, we will discuss LeetCode problem number 445, add two numbers to. This problem challenges us to work with linked lists to perform arithmetic operations while preserving the positional significance of digits. Stick around as we break down the problem and explore effective approaches to solve it. In this problem, we are working with two non-empty linked lists that represent two non-negative integers. These integers are stored such that the most significant digit comes first, and each node in the linked list contains a single digit. Our task is to add these two numbers together and return the result as another linked list, which should also maintain the same format, most significant digit at the head. You can assume there are no leading zeros in the input numbers, except when the number is 0 itself. The input consists of two linked lists, L1 and L2. Each node represents a single digit in reverse order, meaning the head of the list contains the most significant digit. The output will be a linked list representing the sum of these numbers, formatted similarly. Let's explore through examples for clarity. In the first example, L1 is given as 7, 2, 4, 3, which represents the number 7243, and L2 is 5, 6, 4, representing 564. When we add these two numbers, we get 7243 plus 564, which equals 7807. The output linked list is 7807, where the digits of the sum 7807 are stored such that the most significant digit, 7, is at the head of the list. Now, consider the second example. Here, L1 is 2, 4, 3, representing the number 243, and L2 is 5, 6, 4, representing 564. To further clarify, let's consider one more example. If both linked lists represent the number 0, meaning L1 equals 0, and L2 equals 0, their sum will also be 0. The resulting linked list in this case is 0. This example highlights the simplicity of the problem when both inputs have the smallest possible values. It also emphasizes the guarantee that there will be no leading zeros in the inputs, except for this scenario where the number itself is 0. Beyond these examples, the problem comes with several constraints. The number of nodes in each linked list can range from 1 to 100. Each node's value is guaranteed to be between 0 and 9, making this a straightforward representation of digits. Additionally, it is guaranteed that the input linked lists represent valid non-negative integers. The most significant digit is always stored in the first node of the linked list, ensuring that the representation is consistent with the standard positional notation of numbers. While the numbers themselves do not contain leading zeros, except for the case of 0, there are some important edge cases to consider. For example, the two linked lists might have different lengths, such as L1 equals 1, 0, and L2 equals 9. Another edge case is when the sum of the two numbers requires an additional carry node, like L1 equals 9, 9, and L2 equals 1. It's also possible for one or both linked lists to consist of a single node, such as L1 equals 0, and L2 equals 5. Finally, when both inputs represent 0, the result should be a single node with the value 0. These edge cases help ensure that our solution handles a wide variety of inputs correctly. To solve this problem, one of the first approaches we considered is the brute force method, where we reverse the input linked lists. The main intuition behind this is that reversing the lists allows us to process the numbers from the least significant digit to the most significant digit, which aligns with how addition is typically performed. First, we reverse both input lists. Then, we use a helper function to add the two reversed lists while handling any carry, following a process similar to the one used in LeetCode problem number 2. After obtaining the sum, we reverse the resulting linked list to restore the original order of the digits. While this approach is fairly straightforward and has an efficient time complexity of O, n plus m, where n and m are the lengths of the two lists, it does have some downsides. It modifies the input lists, which may not always be acceptable in certain scenarios, and the double reversal, both at the beginning and the end, can feel a bit inefficient. Additionally, although it uses O(1) extra space for reversing the lists in place, this modification can be seen as intrusive to the original data structure. Now, to address the inefficiencies and limitations of the brute force approach, we turn to an optimized strategy that leverages stacks. The key insight here is that stacks allow us to simulate the reversal of the lists without actually modifying them. By storing the digits of each number in a stack, we can process them from the least significant digit, which is at the top of the stack, to the most significant digit. The steps are straightforward. First, traverse the input linked lists and push their digits onto two separate stacks. Then, as we pop digits from these stacks, we add them together along with any carry, building the result list from the least significant to the most significant digit. To ensure the correct order of the result, we can use a dummy head or manage the result list explicitly. This approach avoids modifying the input lists and has the same O, n plus m, time complexity as the brute force method. However, it introduces an additional O, n plus m, space overhead due to the use of stacks. Despite this, the stack-based approach is efficient and avoids the inefficiencies of list reversal, making it a strong contender for solving the problem. Another alternative strategy involves using recursion. The intuition here is that recursion inherently traverses the lists to their ends, effectively reversing the traversal order. This allows us to add the digits starting from the least significant digit at the end of the lists and propagate the carry back up as the recursion unwinds. The steps involve recursively traversing both lists until their ends, adding the digits at each recursive level, and building the resulting linked list as the recursion unwinds. The main advantage of this approach is its elegance, as the recursive stack implicitly handles the reversal without requiring any explicit data structures like stacks. The time complexity remains O, n plus m, as we still traverse each list once, but the space complexity becomes O, max, n m, due to the recursion stack. However, this approach comes with a significant drawback. For very deep recursion, such as when dealing with extremely long lists, it risks causing a stack overflow. As a result, while the recursive approach is mathematically elegant, its practical usage is limited by the constraints of the recursion stack. After evaluating the different strategies, we chose the optimized approach using stacks as the most robust solution. The reasoning behind this choice is threefold. First, the use of stacks aligns perfectly with the problem's requirements to process digits in reverse order without modifying the input lists. This ensures that the integrity of the original data is preserved. Second, the stack-based method avoids the inefficiencies of the brute force approach, such as double reversal, and provides a clearer alternative to recursion, which can be risky for very deep lists. Third, in terms of implementation, the stack-based solution is straightforward, making it easier to debug, maintain, and understand compared to the recursive method. Of course, there are trade-offs. Using stacks introduces an O, n plus m, space overhead, while the brute force method requires only O1 additional space but modifies the input. Recursive solutions are compact and elegant but risk exceeding stack limits for large inputs. Overall, the stack-based approach strikes the best balance between space usage, efficiency, and implementation clarity, making it the ideal choice for solving this problem. In this problem, we are tasked with adding two integers represented as linked lists, where each node contains a single digit and the most significant digit appears first. However, performing addition is simpler when the least significant digit comes first, so we start by reversing the input lists. This is achieved by traversing each linked list and adjusting the next pointer of each node to point to the previous node. A helper function, reverse_list, can handle this reversal efficiently. Once reversed, the least significant digit comes first, and the addition process becomes straightforward. Next, we initialize a dummy node to build the result linked list. This dummy node acts as a placeholder, allowing us to handle the addition process without worrying about edge cases at the start of the list. We use a pointer, current, to keep track of our position in the result list as we build it node by node. With the input lists reversed, we now proceed to add the two numbers digit by digit. To handle carryover between digits, we use a variable carry, initialized to 0. As we traverse the reversed lists simultaneously, we compute the sum of corresponding digits from both lists, along with the carry. From this sum, we determine the new digit to be added to the result list using new_digit equals sum%10, and we update the carry using carry equals sum/10. A new node is then created with the value new_digit, and it's appended to the result linked list. If one list is longer than the other, we continue traversing the longer list after the shorter one ends, adding any remaining digits along with the carry. At the end of this process, if there's still a non-zero carry remaining, we create an additional node to store this value, ensuring the result is complete. Since the result linked list was built in reverse order, we need to reverse it back to restore the original significant digit first order. This is done using the same reverse_list helper function that we used earlier. After reversing, the dummy node is skipped, and we return the actual result list starting from the node next to the dummy. One key insight here is that reversing the input list simplifies the addition process by aligning it with the natural order of addition, allowing us to focus on one digit at a time without worrying about their positional values within the original numbers. This approach not only simplifies the logic but also makes the implementation more intuitive. Carry propagation is an essential part of this algorithm. The carry variable ensures that any overflow from a single-digit addition is correctly passed to the next higher digit, mimicking the way traditional addition works. For example, when adding 9 and 5, we compute 14, append the 4 to the result, and carry over the 1. Another critical component is the use of a dummy node to initialize the result list. This simplifies the process of constructing the list, as we don't need to handle special cases for initializing the head. Once the list is complete, the dummy node is discarded. In terms of data structures, the input linked lists are reversed to simplify traversal and addition. The result is stored as a new linked list, which is built node by node during the addition process. This structure allows for efficient appending and easy reversal to restore the final order. Now, let's analyze the complexity of this algorithm. The time complexity is O, n plus m, where n and m are the lengths of the two input lists. Reversing each list takes O, n, and O, m, adding the digits requires O, max, n, m, and reversing the result list also takes O, max, n, m. Overall, this gives us a linear runtime with respect to the total number of nodes. The space complexity is O, max, n, m, because the result linked list requires space proportional to the length of the larger input list. Additionally, the reverse_list function operates in place, so no extra space is used for the reversal process. These efficiency characteristics make the algorithm well suited for handling large linked lists. Finally, let's consider some important edge cases. When the input lists have unequal lengths, the algorithm handles this gracefully by continuing to traverse the longer list after the shorter one ends, adding any remaining digits to the result. If the final sum produces a carry, such as when adding 9 and 9 with a carry of 1, a new node is created to store this value. For empty input lists, the result is simply the non-empty list, or an empty list if both inputs are empty. Additionally, if the input lists represent the number 0, the result is a single node containing 0. These edge cases ensure the algorithm is robust and covers all possible input scenarios. Here, we begin by defining the list node class, which serves as the building block for our linked list. Each node in the list contains a value, val, and a pointer to the next node, next. Next, we define the solution class and the addTwoNumbers method. The goal of this method is to add two numbers represented as linked lists, where each node contains a single digit, and the digits are stored in reverse order. To handle this, we first define a helper function called reverseList, which reverses a linked list. This function uses a simple iterative approach, where we maintain a previous pointer to keep track of the reversed portion of the list. As we iterate through the original list, we adjust the next pointers to reverse the direction. Once we reach the end of the list, the previous pointer will contain the reversed list. Using this helper function, we reverse both input lists, L1 and L2, so that we can process them from the least significant digit to the most significant. We also initialize a carry variable to handle any overflow during addition, and create a dummy node to serve as the starting point for our result list. A current pointer is used to build the result list as we iterate through the digits of L1 and L2. Now, we proceed to add the numbers represented by the two reversed linked lists. Inside the while loop, we extract the value of the current node for both L1 and L2. If either list is exhausted, we use a default value of 0. We then calculate the sum of these values along with the carry from the previous operation. The carry is updated to the quotient of the total divided by 10, as it represents the overflow that needs to be carried to the next digit. The remainder, which is the actual digit for the current position, is stored in a new node that we append to the result list. We then move the current pointer to this new node to continue building the result. If there are more nodes in L1 or L2, we advance their pointers as well. Once all nodes are processed and there is no remaining carry, the result list is complete, but it is in reversed order. To restore the correct order of the digits, we use the reverse list helper function again on the result list, starting from the node after the dummy. Finally, the method returns the head of this correctly ordered result list. Here, we start by defining the basic structure for our singly linked list, which includes a class called listNode. Each node in the list has an integer value, val, and a reference to the next node, next. The class includes constructors to initialize nodes either with a value or with both a value and the next node. Then, we move on to the solution class where the main logic resides. Within this class, we define a helper method called reverseList that takes the head of a linked list as input and reverses the list. The method uses a pointer previous initialized to null, and a while loop iterates over the list. For each node, we store the next node temporarily, redirect the current node's next pointer to previous, and then move both previous and head one step forward. This allows us to iteratively reverse the list while maintaining access to the remaining nodes. After completing the helper method, the addTwoNumbers method is introduced, which is the main function that adds two numbers represented as linked lists. First, both input lists, L1 and L2, are reversed using the reverseList helper method. This step is crucial because the problem specifies that the numbers are stored in reverse order, so reversing the lists allows us to perform the addition from the least significant digit to the most significant. Next, we initialize a variable carry to track any carryover during addition, and a dummy node to serve as the starting point for our result list. Using a pointer, current, we iterate through the nodes of L1 and L2 while also considering the carry. At each step, we extract the values from the current nodes of L1 and L2, defaulting to 0 if a list has been fully traversed. The sum of these values, along with the carry, determines the value of the new node in the result list. We compute the carry for the next iteration by dividing the total sum by 10, and the remainder becomes the value of the new node. Finally, we advance the pointers for both input lists if they are not null, ensuring we process all nodes. Once the addition loop completes, the result linked list is constructed in reverse order. To restore the correct order, we call the reverseList method one final time on the result list, starting from the node following the dummy node. This reversal ensures that the final output matches the problem's requirements, with digits stored in the original order. The method then returns the head of the reversed result list, completing the implementation. This approach effectively handles lists of different lengths and accounts for any leftover carry, resulting in a clean and efficient solution to the problem. To solve this problem, we begin with the input linked lists representing the two numbers. For example, L1 is 7-2-4-3, and L2 is 5-6-4. Since the digits are stored in forward order, we first reverse both linked lists. Reversing L1 gives us 3-4-2-7, and reversing L2 gives us 4-6-5. This allows us to perform addition starting from the least significant digit. Next, we initialize some variables, a carry value set to 0, a dummy node to help us build the result linked list, and a pointer, current, which starts at the dummy node. These setup steps prepare us to iterate through the reversed lists and compute the sum digit by digit. Now, we proceed to add the digits from the reversed linked lists one at a time. In the first iteration, we add the digits 3 and 4, along with the carry of 0. This gives a total of 7. The carry remains 0, and we create a new node with the value 7, updating our result linked list to 7. In the second iteration, we add 4 and 6, giving a total of 10. Here, the carry becomes 1, and we add a new node with the value 0. The result list now looks like 7-0. Next, we add 2 and 5 along with the carry of 1, resulting in a total of 8. The carry resets to 0, and we append a new node with the value 8, making the result list 7-0-8. Finally, we add 7 and 0, along with the carry of 0, resulting in 7. We create a new node with this value, giving the final result list in reverse order as 7-0-8-7. After completing the addition in reverse order, the last step is to reverse the result linked list to restore the correct order. This gives us the final result of 7-8-0-7. To further solidify the approach, let's look at another example. Here, we are adding L1 equals 2-4-3, and L2 equals 5-6-4. First, we reverse both linked lists. Reversing L1 results in 3-4-2, and reversing L2 results in 4-6-5. With the lists reversed, we are ready to perform the addition just as we did in the previous example. In this example, we add the digits from the reversed lists. In the first iteration, we add 3 and 4, resulting in 7. The carry remains 0, and we create a new node with the value 7. In the second iteration, we add 4 and 6, which gives 10. The carry becomes 1, and we add a new node with the value 0. In the third iteration, we add 2 and 5, along with the carry of 0, resulting in 8. A new node with the value 8 is appended. Once all the digits are added, the result linked list in reverse order is 7-0-8. Reversing this list gives the final result of 8-0-7. Finally, let's consider the simplest case of adding two single-digit numbers. For L1 equals 0 and L2 equals 0, reversing the lists does not change their structure, so we have 0 and 0. Adding these digits together gives a total of 0, with no carry to propagate. We create a new node with the value 0. Since there are no more digits to process, the result list in reverse order is 0. Reversing this gives the final result, which is also 0. This demonstrates that the solution works correctly for edge cases as well. To analyze the time complexity of this solution, let's break it into 3 key steps. First, we reverse the two input linked lists twice. The reverse list function processes each node of the linked lists exactly once. If the lengths of the lists are n and m, the time complexity for reversing both lists is O, n plus m. Since we reverse them twice, once for the input lists and once for the result, the total time complexity for this step remains O, n plus m. Next, we iterate through the reversed linked lists to add their digits. This loop continues as long as there are nodes to process in the two lists or the carry is non-zero. At each step, we handle one node from each list, perform the addition, and move to the next node. This means the time complexity for the addition step is also O, n plus m, as it depends on the total number of nodes. Finally, we create the result linked list during this addition process. For each digit in the sum, we create one new node, which is an O1 operation. Since the total number of nodes in the result list is at most max n plus 1, the time complexity for this step is still O, n plus m. Combining these 3 steps, the overall time complexity of the solution becomes O, n plus m. Now, let's summarize the total time complexity and discuss the space complexity. Adding the time complexities of all the steps, we get O, n plus m, for reversing the lists, O, n plus m, for the addition, and O, n plus m, for creating the result linked list. Together, this gives a total time complexity of O, n plus m. On the space complexity side, there are a few factors to consider. First, the reverse list function uses an iterative approach, meaning no extra recursive stack space is used. This ensures that reversing the lists operates in O1 space. Second, we create a new linked list to store the result, and the number of nodes in this list is at most max n m plus 1, which results in a space complexity of O, n plus m. Finally, the algorithm uses a few temporary variables, like carry, val1, and val2, along with pointers like current, L1, and L2. These variables require constant space, or O1. Therefore, the overall space complexity is dominated by the storage for the result linked list, which is O, n plus m. The total space complexity of the solution is O, n plus m, primarily due to the storage required for the result linked list. Comparing this with a brute force or naive approach highlights why this method is more efficient. In a naive solution, we would first convert the linked lists into integers, perform the addition, and then convert the result back into a linked list. While this approach also has a time complexity of O, max, n, m, it requires additional space to store the integers during conversion. This extra storage depends on the size of the numbers being represented and could be limited by the maximum integer size in certain programming languages. For example, while Python can handle arbitrarily large integers, other languages may face constraints. Our current approach avoids these limitations by working directly with the linked list structure. It achieves the same O, n plus m, time complexity but is safer for large inputs and more memory efficient, as it only uses space proportional to the size of the result list. Finally, let's analyze the algorithm in terms of best, average, and worst-case scenarios. In all cases, the time complexity remains O, n plus m, as the algorithm processes all nodes in the input lists exactly once and creates a result list of comparable size. This holds true regardless of the input values or the presence of a carry. To mathematically prove the big O complexity, we consider the lengths of the two input linked lists, n and m. Each major step, reversing the lists, iterating to add the numbers, and creating the result list is linear with respect to the total number of nodes. Summing the contributions from these steps, we get O, n plus m, plus O, n plus m, which simplifies to O, n plus m. Additionally, the algorithm avoids nested loops and recursive calls, ensuring that the complexity remains linear. This makes the solution efficient and scalable, even for large input sizes. When solving this problem, there are a few common mistakes to watch out for. First, skipping input validation can lead to runtime errors. For instance, if one of the input linked lists is null or empty, you need to handle that explicitly. Next, be mindful of carry handling. During addition, if the sum of digits exceeds 9, the carry must be correctly propagated to the next position. Another mistake is reversing the input lists for computation but forgetting to reverse the result back, which can lead to incorrect outputs. Additionally, assuming the two linked lists are of the same length can cause misalignments. Always check and pad the shorter list with leading zeros to align the digits properly before performing addition. Lastly, modifying the original input lists instead of working on copies can introduce unexpected side effects, especially if those inputs are being reused in other parts of your code. Now, let's look at some insights that are particularly useful for interviews. First, it's essential to have a strong grasp of linked list operations, such as traversing, reversing, and manipulating these structures, as they're foundational concepts that often appear in related problems. Always take time to think about edge cases. Examples include handling lists of different lengths, lists consisting entirely of zeros, or lists with just a single node. If the space complexity is a concern, consider optimizing by avoiding list reversal altogether. Instead, you could use recursion or a stack to simulate the addition process starting from the most significant digit. Clear communication is another key aspect during interviews. Make sure to articulate each step of your approach, particularly when managing carries or aligning digits, as this demonstrates your thought process. Also, practicing related problems can be incredibly helpful. For example, LeetCode 2, which involves adding numbers with the least significant digit first, or LeetCode 234, which focuses on reversing and comparing linked lists, can provide valuable preparation. Let's explore some alternative approaches to solving this problem. One method is the reversal approach, where you reverse both input lists, add them like you would in LeetCode 2, and then reverse the result back. This is straightforward to implement but comes with additional space and time costs due to the extra reversals. Another option is the stack-based approach, which uses stacks to simulate addition starting from the most significant digit. While this avoids explicit list reversal, it still requires O, n, space for the stacks. A more elegant alternative is the recursive method, which leverages the call stack to traverse to the end of the lists and perform addition as the recursion unwinds. This is space efficient and avoids reversing, but it can be tricky to debug and may lead to stack overflow for very large inputs. Lastly, there's the in-place addition approach, where you directly modify one of the input lists to store the result. This can save space, but it's only viable if the problem allows you to alter the input lists, as doing so may not always be permissible. Thanks for watching. Today, we tackled problem number 445, add two numbers 2, and explored how to handle linked lists for arithmetic operations. We hope you gained insights into problem-solving techniques and complexity analysis. Don't forget to practice similar problems and refine your skills. See you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!